Hello and welcome to this video about functions in R. It's really important that you get comfortable writing your own functions in R. It can make your life a lot easier because it can save you from writing a lot of repetitive code, and it can help you write better R code overall. One reason is if you have a repetitive task and you write a function for it, if you discover later that you have a bug in your code for that task, if you had written a function, all you really have to do is fix the function rather than fixing your code multiple times every time you wrote the code. So it can make your life easier and it can help you be a better programmer. So we will be running through this script. It's called functions.r. And this will follow somewhat closely Chapter 6 from Advanced R 2nd edition. So I'm going to start up an R session. And here's our first function. So this is a very simple function. What it does is it takes an input, x, squares it, assigns it to the variable y, and then returns it. So here's the syntax for defining a function. You give it a name. So here's the name we're going to give the function. And then we do assignment symbol. And to the right of that goes the function. So there's actually a function called function that's used to create functions. We tell it inside of curly or round brackets which arguments we want to have the function take in. Here there's just one argument, but we'll see more complicated things later. And then after we close the round bracket, we open curly braces. And inside of the curly braces goes the code that you want to evaluate. And usually the code will involve the function argument, in this case x. And this is optional, as we'll see, but you can specify a return value. And then we close the curly brackets. So what this does is going to define a function square that will take in a number x and return the square of x. So when we run this piece of code, what we're doing is we're defining the function. We're not actually calling the function. We're just saying that there's an object now called square that we can refer to. So to prove that to you, I'm going to run this. And what gets printed out is the function definition here on the right. And now we can call this function square just like we call any other function that's available to us in R. So we put in round brackets the input 4, and we say square of 4, and that gives 16. So what it's doing is it's taking this number 4, it's applying this code to it, and then returning y. We can also do, all the things you can usually do. So we can assign it to a variable and print that out. So one of the most important things to understand about functions in R is that functions themselves are objects. So after we define this function square, we can pass it to another variable. So I say fun equals square. And now we can call fun, and it does the same exact thing. So R is some people call it a functional programming language. And functions play a special role in functional programming languages. All right. So in R, there are 3 parts to a function, formally. The first part are called the formals. The formals are just the arguments to the function, and there's a function in R called formals which returns the argument. So if we run formals on square, we get $x. So what this is going to return is a list of the arguments. The second part of the function is the body. So the body is the body of the function, what happens inside when you call the function. This is the code. This is actually kind of a weird type of R object that we're not really going to get too much into in this course. but this is a R language object. And if you want to read a little bit more about that, you can look at the documentation for body. The third part of a function is called its environment. And there's a function called environment that tells us something about the function's environment. So what this returns, if you could see on the right here, is environment colon R global environment. So this is the argument that we're kind of in when we're working in the console. If I just type environment, we get the R global environment. The environment of a function is the environment in which the function lives, or where the function was defined. So we defined square in this R global environment, and therefore its environment is our global environment. Like I said, functions are objects just like any other object in R. And therefore, functions can have attributes. So we look at the attributes of this square function that we defined. The only one it lists is something called SourceRef. And if we want to look at what that attribute is, we call the attr function with square as the first argument and SourceRef as the second argument. So this returns the source code for how we define the function. One kind of minor thing that differs from the body, so if we run body again, you can see it strips the function of its comments. So sometimes it can be useful. You want to see what the comments are in the function to give you a little bit more information. If you look at SourceRef, that will retain the comments. Okay. And we can also set our own custom attributes. As I mentioned before, some R programmers make heavier use of attributes than other R programmers. I'm a person that doesn't use them that much, but some people do. So you can set your own custom attributes for functions just like any other object in R. So we want to tell people that this is a polynomial, and now when you print out the attributes, it will print out that it's a polynomial. Okay, so there are some shortcuts to make your function definitions a little bit more compact. So the first one is that the return value of a function, if you don't specify it with the return function at the end of your function, is just automatically the last object that gets evaluated. So the return value can be omitted in some cases. So if we define this function, it's going to return y. We can't see that. We'll see in a second why not. But if we had said a equals square 3, and then we print out a, we'll see that it gave 9. Okay. As a matter of style, when I write functions, I usually explicitly include the return value. You don't always need it, but I think it can help the other programmers to see exactly what your function is giving back. All right, another shortcut is you don't actually have to do that assignment to y in this case. You could just have a one-line function that just returns x squared. So there's no need to define an intermediate return object. So if we run this, it just gives 9. Since you don't have to specify the return value, you can just say x squared here. So this is an even shorter function definition. And this gives the same thing. Just like with if statements and for loops, if your function only has if the body of the function only has one line, you can keep everything on the same line. So here, it's just return x squared, so we can do this, and this works just fine. You may prefer to write, very simple functions like this. If you have a lot of them that you're defining and you want to keep the codes more compact, this can be easier to read. And the last thing is also if it's only on one line, if there's only one line in the function, you can omit the curly braces. So this is true of if and for as well. I like to usually keep the curly braces. That's a matter of style. I have no problem reading this and determining what is getting defined here. So just as a general recommendation, make sure it's clear when you write the code what the function does and what it returns. And there may be some differing styles among different programmers for exactly how to do that. All right, so as we saw above, sometimes the function will print out a return value when you call it, sometimes not. So let's just look and see what those rules are. So a function will never print out a return value when you assign it. So if you do this, nothing happens. Well, something happens. Square of 3 gets assigned to z. You can see that z is 9, but nothing gets printed out. Sometimes the calling a function will print something out and sometimes not when you just call the function and don't assign it. So let's look at this example. So I've defined the function this way. If I do square of 3, it prints something out. If I do this, if I have one line where I assign x squared to y, it doesn't print anything out. You can see on the right side it didn't print out the 9. The function still works. I can say square of 3 equals z, and z is 9. But when you define the function this way, where the last line is an assignment, it doesn't print anything out. If you add a line, so I did, by the way, you can write multiple statements on one line in R, but you have to separate them by semicolons. So here I have 2 statements and separated by a semicolon. So this is perfectly legal to do in R. And the way this differs is I do this assignment, but then I print out y at the end, and this will automatically print out y. So if you're calling a function and nothing's getting printed out, that could be the way because of the way it was defined. And here's some simple rules for when it gets printed out and when it doesn't. Now let's look at some more complicated examples. The square is a great function, but it's not really going to get us very far. Here's a function definition that does something a little bit more complex. So I'm defining this function called Center1. So that's the name of the function. I do the assignment operator, and then I call the function. And this function is going to have 3 arguments. The first argument is a vector of numeric values, x. The second argument is a character string. And this argument differs from the first argument in a couple ways. The main way is that I'm naming the argument fun, and I'm giving it a default value. We'll see how this works in a second. Basically, what this is going to allow us to do is to call the function without specifying this second argument, and the third argument for that matter, and it will still plug in these default values. The third argument is a number p. So let's see what the function does. So there's a big long if-else statement with 4 possibilities. If fun equals mean, which is the default value, what Center1 does is it takes the vector x, subtract off the mean, and assigns to x0. So if that's true, then it skips all this stuff and it just returns x0. Otherwise, it checks whether the function is median, then it subtracts off the median. Otherwise, it checks if it's quantile, and it subtracts off the pth quantile of the vector x. And then otherwise, it says, I don't know what to do. You didn't give me mean, median, or quantile, so I'm just going to throw an error. Okay, so let's call this code, which defines the Center1 function. And let's give it a test vector. So here's y. I just took the numbers 1 through 9 and squared them. Just to see, the mean of that vector is 31.6667. And if I call Center1 on that vector with fun equals mean, you can trace through what's going to happen. It sees that fun is equal to mean, and it subtracts off the mean and returns x naught. So what did it do? So let's compare these. Let's do cbind y Center1 y. All right, so it did the conversion from this vector to this vector. Remember, the mean was 31, so this kind of makes sense that these values are negative, these are positive. Okay. Now, since mean was the default argument for fun, we can omit that one, and this should give the same answer. All right. Let's look at the median. The median's 25. If we call Center1 with fun equals median, we get this. So notice there's a 0. If we look at y again, there's a 0 when the y was 25, makes perfect sense. And then say we want to look at the 0.25 quantile and subtract that off. That number is 9. We call this. All right, let's see what happens when we call this. So we say Center1 y fun equals quantile. And let's trace through what happens. We didn't specify the p argument, so it's going to be set to its default value of 0.5. We skipped this because it's not mean. We skip this, and then we land on this if statement. And then we subtract off the pth quantile. So when p is 0.5, that's equal to the median. So we're going to do x minus the median in that case. What is the median? Median, oh, we already ran that, 25. So this should give us the same as this one. And it does. Now we can override that default and say I want to subtract off the 0.25 quantile. And of course we get a different answer. 0.25 quantile was 9, which was the third element of y. Now when we're programming, there's often many ways to do the same task, and sometimes they're more or less good. Sometimes some ways are better than others. One kind of undesirable thing about our Center1 function is that we have to run through all these if statements and else if statements. And if we wanted to add more possibilities for different types of things we could subtract off, we'd have to go and modify the function and make an else if for each possible value. This could be kind of undesirable if you want the function to be really flexible. So one thing you could try doing is having the user pass the function itself as the argument. So let's see what's going on here. So Center2 is going to be another function. First argument is the same. Now the second argument is fun equals mean. So what is happening here? On the left side of these equal sign, that's just the name of the argument. These are, by the way, these are not quoted. And then on the right side is mean. So what is this? Mean is not the string mean. It itself is a function. Now this looks a little bit different than other functions like square that we printed out. This is what's called a generic function in R. We'll talk a little bit more about that later. So it doesn't actually print out the source code. There's probably like a mean.default, which has the source code. So we'll get into, this is one of R's object-oriented programming implementations. So mean, the point is mean is a function when you specify it this way. And this is perfectly valid. Like I said, functions are objects. We can do all the things you can do with other objects, like passing them as arguments to other functions. So this is perfectly allowable. And then we still have a third argument, p equals 0.5. So when I run this code, I've defined the Center1 function. There it is. And this function is a lot simpler. It's basically 2 lines. It really could be 1 line. I could get rid of that if I wanted to, but I'm going to keep it because I like to include the return value. And that's it. So if we call Center1 y, it's going to use the default value of mean. That vector should look familiar. If I do Center1 y median, it subtracts off the median, which was 25, I believe. However, if I do this one, I get an error. So what's happening here? I'm doing x0 is x minus fun of x, where fun is the function that we passed. If I try to do, so quantile is getting mapped to fun, so it's calling quantile of x, quantile of y, because that's the value we're passing to the function. And it gives that vector. So by default, when you call the quantile function, it gives the minimum and then the quartiles and then the maximum. So this is actually a vector of length 5. And what R is trying to do in this line is it's doing y minus quantile y. So it's trying to subtract a length 5 vector from a length 9 vector. And it's giving a warning saying that's probably not what you want to do. So the issue here is we haven't specified the arguments to fun. So quantile is a little bit different from mean and median in that it, for our use case here, requires us to specify which quantile we want to subtract off. So this is a nice simple function, but it actually doesn't do what we want it to. So we need a little help here. Now R has a very special syntax for helping us in this particular case. What we really need is we need to allow the user to pass additional arguments to our function that we're defining that can then be passed along to the function that we're calling. And the way R implements that is it's very kind of innocuous looking in the specification of the function. You just put ... So what this is saying is we want to allow the user to pass other arguments, and then any other arguments that it passes we can pass on to other functions by including ... Okay, so this is actually really a very minor modification to the code, but it actually makes this function a lot more flexible. So let's define this thing. And if we do Center1 y, this will just subtract off the mean. So what happens here is it sees the argument y. By the way, if a function has no default value, then it's a required argument. If we try to call Center1 without an argument, it'll give us an error. It says argument x is missing with no default. So if there's no default value, you have to specify it. So we do this, it says fun equals mean, subtracts off the mean. If we do this, it says fun equals median, subtracts off the median. And if we want to subtract off the median using the quantile function, we'll specify probs equals 0.5. So what's going to happen here is this is an extra argument that gets stored in this ... thing. And then that extra argument will get passed to fun here, which is equal to, in this case, it's going to be quantile, to specify which quantile we want to look at. So if we do this, we get that. So it subtracted out the median, which was 25. And then if we subtract off the 0.25 quantile, it subtracts off 9. Okay. So this is really nice because now we have a pretty simple function. It's really just one line. We added the extra return line. And it's very flexible in that we can pass additional arguments that can be passed on to whatever function we want to evaluate. There is yet another way to do it. I bet you didn't think centering a vector was such a complicated operation. But there is another way to do it. There's a function in R called DoDoCall. And the way DoDoCall works is you supply a function. I believe, let's double check this. I believe this could be either a function object or a character string. Let's double check that by checking the documentation. So here's the documentation. First argument is what. That means what function are we going to call? And this, yes, this can be either a function or a non-empty character string naming the function to be called. So what that means is I could have written mean without quotes here and it will work the same. And then the second argument are which arguments you want to pass to the function specified in the first argument. So here we have y. And what we want to, I want to do mean of y. But I want to use DoDoCall to do it. And this is how you do it. You say mean, and then you specify any arguments inside of a list. So this will just return the mean. If there are multiple arguments to the function you're specifying, you just put them as arguments in the list. And you would name them if they're named arguments. Okay, so that gives the 0.25 quantile. So we can write yet another center function that uses DoDoCall. So we're saying the function is a string mean, and we can also use ... And we're going to do argument minus DoDoCall of that function, and then we're going to specify the input vector, and then any additional arguments that we pass via ... are going to go in that list. Not all functions allow for ... So you have to specify that you want to allow it. A list is one of those functions. See, it explicitly has the ... in the documentation. Okay, so let's define center4, and I'll just prove to you that it does what I'm saying it does. So that's subtracting off the mean, that's subtracting off the median, and that's subtracting off the 0.25 quantile. Okay, now I printed out some, you'll notice in the function definition, I told it I wanted to print something out. So that's why there's extra stuff printed. So let's see, I'm printing out the list of arguments that we're passing to the function. So in this case, the only argument that we were passing was x, which was unnamed in the list. In this case, it's the same thing. In this case, we have an unnamed argument x and then a named argument probs. Okay, so this is just the object that's getting passed in DoDoCall. All right, so things can get slightly complicated when a function has a lot of arguments. We'll see how this works with the plot function in a second, which is one of those functions. Now, there are specific rules if you're specifying multiple arguments on how they get mapped to the actual function arguments. So let's look at this example, and let's pull up the documentation for seek. Actually, let's see if we can pull it up here. Okay, good. So on the right side, I have the documentation for seek. And seek has a bunch of arguments from, to, by, length.out, along.width. So if here I'm calling seek, and I'm not specifying names for the first two arguments, and I am specifying a name for the third argument. So what happens is R will assign this argument 20 to length.out, and then it's going to look at the unnamed arguments, and it's going to put them in order according to the order here. So it's going to assign 20 to length.out, and then it's going to assign 0 to from and 10 to to, and then it's going to assign all the other ones to their default values. Okay. So if we do this, it should give 20 numbers between 0 and 10. Okay, that looks good. If we call this way, so what it's going to happen is it's going to, let's look again at the documentation. There are no named arguments, so it's going to assign 0 to from, 10 to to, and 0.1 to by. So this should give a sequence of numbers between 0 and 10 separated by 0.1. Okay, so that's what it did. So it's important if you have a function like that to be clear which arguments or values are getting passed to. It's probably a good idea to specify, like here, it's probably a good idea to say by equals. So someone reading your code is familiar with the seek function but doesn't remember the exact argument order will know that you're assigning this to by. But this works as well. All right, so let's take a look at the plot function actually, because the plot function is a lot more complicated, just to see another example. All right, so I'm defining y as x plus some error, and I'm going to call plot xy. All right, that brings up a nice plot for us. So let's look at the plot documentation, and let's get it on the right side. Oh. Okay. So plot has a lot of arguments. And if we do plot xy, I've not named either of them. So it's going to obviously assign x to x and then y to y, because x is the first one and y is the second. If I do xyo, it's going to assign O to type. So we can run that. It'll do one of these plots with lines and circles. If I do this, so this gets a bit complicated. So here I'm naming one of the arguments. I'm naming the xlim argument. That tells us how to define the horizontal axis. So what it's going to do is it's going to assign 0.20 to the xlim argument, and then it's going to go back over the unnamed arguments and put them in order. So it's going to assign x to x, y to y, and the third argument was O, so that gets assigned to the type argument. Now again, if things become unclear, it's probably a good idea to just name the arguments, and then anyone reading your code can know exactly what you intended to do and what the code will do. So this works. This is probably better. Now, one of the most important concepts to understand when working with custom-defined functions in R is how what's called lexical scoping works. So these are the rules that determine how R looks up the values of objects. So let's just jump in and look at a couple of examples here. So I'm going to assign the value 2 to x and 3 to y. And then I'm going to define a function that takes in an argument that's called x and returns the product of x and y. So let's define that function and let's call the function and see what happens. Actually, it's probably a better idea for you to guess what's going to happen before I run it. So I'll wait a second here. And now let's run it. So it returns 12. So let's see what happens here. When the function gets called, it sees these two variables, x and y. X is an argument to the function, whereas y is not. So when the function gets run, it looks up the value x from its argument, and then it looks for the value y. It sees that y was not passed to the function, and then it has to look elsewhere to see what y is. And we'll see what happens is it looks one environment up, and it sees that we have we have y defined in the global environment, so it just pulls this value. So what happens is when you change the value of y, and you call this function again, times y, and here I'm setting x to 3. Actually, there's no reason to do that. Let's just keep it at 4. It's going to see that x is 4, and then it's going to look for y, which is now 8. So it should return 32. And it does. Okay. Now, when a function is called, this all has to do with environments. When a function is called, it records the environment that it was defined in. So, when a function is defined. So the environment of times y is the R global environment. That's where it was defined. But the environment will change inside of the function when the function is called. So what the purpose of this function is just to print out all this information about the environments. So it's actually the exact same function in that it returns the product of its argument and y. But I'm printing out various information about the environment. So E1 is going to be the environment inside of the function. E0 is what's called the parent environment. So environments have this hierarchical nested structure. So every environment will live inside of another environment. So if we look at the parent environment of E1, we're going to assign that to E0. And then I'm going to print those two things out. And then I'm going to print out the objects available in that environment, which can be printed out with the ls function. If you haven't used the ls function before, normally how it's used is if you just say ls without an argument, it assumes the global environment, and it prints all those things out that we've defined. Okay, but you can also give a specific environment, and it will print the objects in that environment. All right, so let's redefine times y, and let's run it. So times y3 should return, let's see, what's y equal to? Y is equal to 8 at this point. Y is 8. So this should return 24, but it's also going to print out a bunch of useful information. Okay, so this is the functions environment. Now, function environments are kind of temporary environments because you call the function, it creates an environment while it's running the code in the function, and then that environment goes away. So what R does is it assigns it this kind of string of letters and numbers. The parent environment is the global environment. So you can think of that as one level up from the function environment. So what's happening here is, it prints out the things. So these are the objects available in the functions environment, E1. So it has x, and then the other two objects we defined were E0 and E1. And then these are the objects available in our global environment, which is the parent environment. It has all these different things. So the order of operations here is when it evaluates x times y, it sees that x is available in the function's argument. And then for y, it sees y is not available, and it looks one level up in the parent environment to the function's environment, sees it here, grabs the value, does this multiplication, and returns it. Okay. And then you can see how this works if I remove y and run this again. Now this time it still doesn't see y in the function environment, and now that I've removed y from the global environment, it doesn't see it there either, and it says object y not found, which is what you should expect to happen. Now things can get really complicated when you start doing things like having functions return other functions with respect to what these environments are. So let me just show you. We're not going to get too deep into this in this course, but I want you to be aware of these subtleties just so that you know to be careful when you start doing things like this. All right, so here's a function, f. All it does is it prints out the function's environment, and then it returns a function. So again, functions are objects, and therefore they behave like any other object in R. You can have a function return another function, and here's a very simple example. Okay, so if I run that, I have f here. And let's look at the environment of f. It's the R global environment. The reason for that is that f was defined here in the global environment. Now, if I call this, so what's going to happen? So I'm calling the function f. By the way, this function has no arguments, which is that's allowable. I'm calling the function f and assigning it to g1. So g1 is going to be the function which returns the square of its argument. So let's run this. You can see when I call the function f, it prints out an environment that's 0x55a, yada, yada, yada. And if I look at the environment of g1, it should be the same thing. So because g1 was defined in this function's environment, the environment of g1 is that function's environment. If I run this again, it prints out a different environment. It starts with 0x55, but these numbers are different. That's because when you call a function, it creates a temporary environment, so it's going to be different every time. And therefore, the environment of g2 is different from the environment of g1. Okay. So far, that's not too complicated. When it really gets complicated is when you have functions, it returns a function that has to look up an environment to see the value of the function. So here are some examples. So this is our x times y example. So f1 is going to be a function that returns the function x times y. If I set y equal to 3 and I call f1 of 3, so this is going to set x equal to 3 in this function's environment. And if I call g, it's going to return 9. So that makes perfect sense. Now, if I change the value of y, the return value of g changes. Okay, why is that? So g is a function x times y. It's going to look in, so x is supplied, so it's going to look in this function's environment. Actually, there's two levels here. X is not available in this function's environment, so it has to look up a level, and it grabs x from the function's environment. So that's one level up from this function's environment is one level up from this function's environment, and this function's environment has x, so it grabs x from there. Now it has to look for y. It's not available in this function's environment. It's also not available in this function's environment, so it has to look up in the global environment. And the value is 3 there, so you get 9. If I change it to 4, it looks up in the global environment, sees it 4, and then it'll give 12. All right, so here's something a little bit different. It's similar, but we're multiplying x times y inside of this function and then returning z. So it's still going to return the product of x and y, but the behavior is going to change, and we'll see why in a second. All right, so I set y to 3. I call F2, which generates a function G1, and I call this. So this should give 9. That's good. If I change y to 4, and I call it again, I still get 9. So let's analyze what happens here. G1 is this function. It has a single variable z. Z is not available in this function's environment because it's not passed. So it has to look up a level and sees that z is equal to x times y. And what differs here is z is equal to x times y at the time that this function was defined. So here it was when I defined G1, y was equal to 3, and therefore G1 is always going to return 3 times 3 is 9, even if I change y. The difference is I'm not looking for a variable called y here. I'm only looking for a variable called z. So, and R is not remembering that z was equal to x times y. It's just looking for the variable z. So that's why the behavior differs there. Now, if I redefine a new function when y is 4, now it's going to do what I want and give 12. So again, this is kind of complicated stuff. If you really want to analyze what's going on, it makes sense to add these print statements like up here to print out the environment and list the variables available. And when you start writing functions that return other functions, things get pretty complicated. So please be careful when you do this. And if you see some unexpected behavior, it could be due to how the lexical scoping works in these cases. Okay, that's it for functions.